Okay, so this is section 2.3, but we're going to use it as a precursor sort of review up into section 3, which is the mathematical applications of rational functions. This section is graphing rational functions and behaviors. Now, rational functions, you might be like, what the hell is that? That's just a function that is made up of a function divided by a function. You still might be saying, what the hell is that? Well, it just means you have a function that looks like, say, x squared plus 5x plus 6 over x squared minus 2x minus 3. So you have two quadratics, one divided by the other. That's all I mean. And it doesn't have to be a quadratic. You could have this, right? You could have a 1 on top. You could have just an x on top, right? So it just means you basically have a fraction made up of polynomials. Now, domain. If you discussed domain in grade 10, awesome. If you didn't, here's a refresher. Domain refers to all possible x values, where if you were to pick a random point on your axis, you can track up to somewhere on your graph. Now, your graph might be a parabola, your graph might be a weird curve, your graph might be a straight line. The domain just means if you pick somewhere on the x-axis, you have a corresponding point on a graph. That is the domain, because there are places where your graph will not exist. And those places are common in a couple scenarios. When you have rational functions, it's when the bottom is equal to 0. It's not allowed, right? You can't divide by 0. So what you're doing is you're solving, well, when does x plus 2 equal 0? Well, when x equals negative 2. So that means x can't equal negative 2. And if you look at this example, you want to know when does that equal 0? Well, that, if we factor it, it's x minus 3, x plus 3. And if either one of those equals 0, the whole thing equals 0. So x can't be plus or minus 3. So you'll see you start to get a restricted domain, values for x that are not legitimate, that are not allowed. Okay? That's going to be important moving forward. The next thing we want to know is, what is the behavior of a graph as we either approach infinity, as x approaches infinity, or as x approaches that 0 point. So if you have the most basic function, 1 over x equals 0 is not allowed. So what happens as we get closer and closer and closer to 0? So look at it as coming from the negative side and the positive side. So if x is 1, 1 divided by 1 is 1. If you get closer and closer to 0, if x becomes 0.1, if you divide by 0.1, you get 10. If you divide by 0.01, you get 100. If you divide by 0.0001, you get 1,000. So what you can see is, as x gets closer and closer and closer to 0, because this number is getting smaller and smaller and smaller, this number gets bigger and bigger and bigger and bigger. So as x goes to 0 from the positive side, that's what that means. The y value, f of x, approaches infinity. Now you're going to see what that looks like graphically in a few minutes. And then if you were to key it in as x approaches 0 from the negative side, now it doesn't mean it's going negative, it means it's coming from the negative side. So you go from negative 1 to negative 0.1 to negative 0.001, and right, you're getting closer and closer and closer to 0, but from the negative, this number gets infinitely large, but in a negative direction. So what does that look like? Looks like this. As we get closer and closer to 0, right, from a positive direction, our y value, our output, went to infinity. It's going infinitely up, but it's never going to touch 0. And that went infinitely down, but it's never going to touch 0. That is what we call a vertical asymptote. Okay, it's never going to touch it. Vertical asymptote. Now you also have a horizontal asymptote, and you'll see here as x goes to positive infinity, so if x goes this way, right, if you take your function here, it means as x gets infinitely large, right, 1 over like a gajillion, it's not even a real number, 1 over a huge number is going to be a very, very, very small number. which gets infinitely close to 0. And same from the negative, it's going to be a very, very, very small negative number. So you can see as it goes to infinity, it gets infinitely close to 0, but it will never cross it, never touch it. Now, one special thing about a horizontal asymptote. Horizontal asymptotes are as x approaches positive and negative infinity. Because you can cross a horizontal asymptote, which I'll show you in a little bit, but you will never cross a vertical asymptote. But a horizontal asymptote only matters as we approach infinity, as we go infinitely that way and infinitely that way. So, here's another example. Graph this function. Well, what is x not allowed to be? You can see right here. X is not allowed to be 1. So you put your vertical asymptote right here. X is not allowed to be 1. Now, it helps here if you consider this as a downward shift. Now, you might be okay with that, but you might not. You could also get a common denominator. And negative 1 is equal to x minus 1 over x minus 1, because that is 1. So you could say you have 1 minus x minus 1 all over x minus 1. So 1 minus x plus 1, which gives you x, negative x plus 2 over x minus 1. Now you'll see later how this gives us a horizontal asymptote, but this is a downward shift. Now don't stress too much about this right now, but here we go. Boom, boom, boom. You'll see on your grid this is actually at 1 because look at your scale. So you have a horizontal asymptote as you approach negative infinity, positive infinity. Here, what is x not allowed to be? Boom, negative 2, vertical asymptote. And you have a horizontal asymptote as x approaches 0. But now, how do we know that, right? We haven't shifted our graph up or down, and you actually haven't learned about shifting of graphs. Nope, you should have in grade, trying to remember here. No, we're going to talk about shifting soon, so don't stress about that right now. Maybe mainly focus on vertical asymptotes right now, because now when we get to vertical asymptotes, we know that it's because it's values that will make 0, right, in the denominator. That'll give us a vertical asymptote. Horizontal asymptotes, though, remember that it's as you approach plus or minus infinity. So there's a little shorthand to this, and it's this. You see here you have g of x on top and h of x on the bottom. If the denominator has a higher degree than the numerator, the asymptote is 0. If the numerator and denominator have the same degree, you divide their leading coefficients. I'm going to show you examples of all this. But if g has a higher degree than h, if the numerator has a higher degree, you have no horizontal asymptote. So looking at an example. First one, same degree, right? Leading coefficient is a 3, leading coefficient is a 1. We don't write it. So you have a horizontal asymptote at 3. Here, denominator has a higher degree, so you have a horizontal asymptote at 0. Here, numerator has a higher degree, no horizontal asymptote. Now, how do you calculate, how can you show that mathematically? This is a little precursor into calculus and pre-calculus. If you took this and you divided every term by x, you'd have 1 over x over x over x over 1 minus x. And now if you consider, because remember we're talking horizontal asymptotes, if you consider as x goes to infinity, so as x gets very, very, very big, well 1 over a very, very, very big number is essentially 0 because it's such a small number. So this would become 0 over 1 minus 0, which is 0 over 1, which is 0. That's how you get your horizontal asymptote, right? And that's from this. The degree is bigger on the bottom than it is on the top, so the horizontal asymptote is at 0. And we have a vertical asymptote at 1. Here we have same degree, right? So a horizontal asymptote is the leading coefficients. Boom, 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 boom at 2. To show you that other way again, divide everything by the highest degree power of x. Now, as x gets, those cancel. You now have 2 over, as x gets incredibly large, 1 minus 0, so it's just 2. Boom. Okay. Another example with matching coefficients, but there's no vertical asymptote because this will never equal 0. Here we have to factor, right? Factor this quadratic to get our asymptotes. It's where x equals 2 and x equals negative 1. So you draw in your vertical asymptotes. Boom, 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 boom. You draw in your vertical asymptotes. Your horizontal asymptote, higher degree on the bottom, so it's at 0. And then you just map the behavior of your grid. So here you've seen I've plugged in values of x into my function in order to see the behavior. Now, do you need precision in this at this point in this grade? No, but you will in grade 12 and you will further ahead. And then here's one more example. You get a funky graph. Now, you see here, you got vertical asymptotes at 0 and negative 2. So you can see there's one here and there's one here. And you have a horizontal asymptote, right? Same power, so leading coefficient, so you divide by 1. You have a horizontal asymptote here. But now you might notice something strange. Now here they approach, yes, and here they approach. But this graph goes through my horizontal asymptote, and I thought that it was not allowed. And that's where I said you can cross a horizontal asymptote as long as you're not the x value moving towards infinity, right? Because this isn't going to infinity. It's getting infinitely close to 1 and infinitely close to negative 2. But these ones that are going to negative infinity and positive infinity will never cross the horizontal asymptote. Lots going on here. I'll do a bonus video for this, try and help smooth this out, but try your best. This is a good visualization practice for moving into grade 12. All right, take it easy.